think I have 49 in here. So just take one and pass it along the line. This is whole one so that hopefully you don't lose it. If you want another copy, it's on the web so you can print it out from there.
Yeah.
So I'm only going to do this twice. So all of the stuff that you get into the full semester.
If I stuck with this one, no way. What difference?
Characteristic is in the process, which is
Machine process.
I tried to 3D print something for my brother. Metal work and stuff. That's really it's just different.
can't put it on.
It gets big like that. The bottom pulls too much. Stuff is doing it. Makes in my class, and then it gets help create it.
This is all around that.
Charge will be initial charge plus integral of IDT without power.
QDT is
No charge, yeah. It's the initial charge plus change in charge over from 0 to 3.
chapter 2.
For that one, integral of IDT is charge. So it's Q over charge, Q over I. And you might choose.
They're going to keep going.
Apparently.
Anybody not know what an NQA coupon is? I know the question always comes up. If I don't use one, can I get extra credit? No. No,
He didn't grab a check. Oh, he
This is
is.
the equation sheet for the semester. It's in fluorescent green. You can't lose it, hopefully.
Watch me.
Really?
I lost some points. Can't lose them.
I'll stay with this spot. Just going to the lecture room.
So as this stuff is coming around, let me just talk a little bit while this stuff is being passed. Let's talk about problem solving. Are there solution manuals out there? There's absolutely solution manuals. There's a good way to use the solution manual, and there's a bad way to use the solution manual, right? The good way is that you actually attempt the problem. You actually try your best to do the thing. And let me tell you, any problem that I give you, you should really try on your own and not let somebody else do it for you. Because when you take the quizzes and the exams, you got that person with you. And you don't have a solutions manual too. Okay, so you gotta remember, a bad way is to go to the solutions manual first, and then write down the solution. Plus, they solve those problems like dumbasses, as far as I'm concerned. They do some of the most craziest things, and you go like, why would you do that? I look at that solution, Tim's gonna look at that solution, he's gonna say like, that's a no-brainer. You should get a 0 for that problem. And it's under my direction that he gives you a 0. Okay? You gotta attempt it, and you'll see that this is where I radically differ than the textbook, especially for the first few chapters here. You should save those NQA coupons. I'm gonna laugh at you if you turn it in for the first problem set. I'm not kidding. Because wait until chapter 8 and 9. Wait till chapters 4 and 5 come. Then you could say, I shouldn't have used those coupons. Save them for the more challenging chapters. Okay? Now those challenge problems that I put on the problem set, I know there's solutions for that out there. I can Google things. But I'm going to give you something similar to those on the quiz. So if you can't do those on the homework, you stand no chance on the quiz. You gotta attempt it, right? You gotta struggle with it. That's what you gotta remember. You gotta struggle with the problem solving to actually get there. And what you're gonna find here is that this course starts off fairly simple. Chapters 1 and 2, as far as I'm concerned, they're really reviewed. And there's some notational changes, and that's one of the things that we'll have to introduce. So you'll see chapter 1 and 2 go like this, and then I'm gonna work as hard as I can to make chapter 3 as hard as I can. And all of a sudden, you're gonna see a spike. And that spike is important, because when you get to chapter 8 and 9, and even 10, if you can't do what I call simple circuits, you might as well drop the course then. That's why I have to make chapter 3 as challenging as possible. It actually builds your intuition for how linear circuits behave. And if you, in EE, this will really help you in the second part of this course here. And then it sort of like goes in the, like, it starts to increase in difficulty. And when we get to 8 and 9, that's when it really gets really steep. So that's why I said, save those NQA coupons. Okay, I think we're done, right? Let's go, chapter 1. Did we get out of it?
You adding to it? No, it's actually really that's how you are better.
So what we're looking at here is we're essentially looking at circuit. You're going to find out that in circuits, there's really only 2 questions we ask. What's the current? What's the voltage? Okay. Sometimes we'll ask the power, but the power depends on voltage and current as well. And what you're going to find here is that the type of circuits, the type of circuit that you see depends on 2 things. Okay? So, how do we say this? The type of circuit will dictate the type of problem solving. So the first thing that you'll find here is it depends on the type of element. And as you already know, that the most common types of elements that you saw in 4B, which is a resistor, capacitor, and inductor. And they all have resistivity, capacitance, and inductance, and they all act the same way. Okay, so when you look at these guys, you'll see that we got R, L, and C, and then we have voltage and current sources. And you don't know what a current, my experience is that you don't know what a current source is. And that's a pretty counterintuitive, thing in the beginning, but once you get to it, you'll get used to it. Now there's other types of sources here. What you saw in 4B was independent sources. We're going to deal with these sources called dependent sources. And typically dependent sources are an integrated circuit element. And so you'll see that a dependent source typically has 6 terminal points instead of 2 terminal points for a voltage source. And we'll get to those as we come along here. So it depends on the type of element, and the other thing that's really important here is in the geometric structure. That means, is it series, parallel, or not series? Parallel. And what you're going to see here is that when we talk about series and parallel, that really is sort of like what chapter 3 is about. But not series and parallel, there are techniques that we could modify from physics 4B that will make it a hell of a lot easier to do that. And you'll see that those go under the name of node and mesh analysis. And what they do here is that we effectively take Kirchhoff's voltage and current laws and we modify them to make circuit solving actually fun, believe it or not. They become quite trivial. But you'll see that we'll start to increase the complexity of these circuits here. But that's the only 2 things that they depend on right there. And so that means then, when we go to a circuit, depends on which chapter we're at. We got one of these, or 2 of these, or 3 of these. And then we talk about what happens in here. And you'll see where it becomes super important in series and parallel is when we get to RC, RL, or RLC circuits. And that's why I gotta really stress chapter 3 quite a bit. So since we're talking about current and voltage here, let's just go straight down the line. Let's start with current here. So I'll just briefly review what I think about current here, just to sort of like, I don't know, dust you off from last semester or however long it was that you took 4B here. So when you look at current, the concept of current really is about what? It's about the structure of the atom. So when you look at the atom, we could treat it as a classical atom. If we treat it as a classical atom, you can use Gauss's law. And Gauss's law just says what? Charges outside an enclosed, what is it? What's it called? This Gaussian surface don't affect any of the charges inside. But unfortunately, the atom is not a classical atom. It's a quantum mechanical atom. So Gauss's law is a rough approximation of what you could do that. But what you'll find here, so if I look at atoms, we could talk about charge screening. And we could say that this is approximately, we could think about Gauss's law. We can't really use Gauss's law because as we find when we look at shells, you could have electrons moving from one shell to the next, you know. And in fact, they do that. There's a probability that that would happen. And then we got to look at the distance of electrons from nucleus. And essentially what this really tells me is that it's almost like Coulomb's law. So I say approximately because they don't really hold. Gauss's law won't hold for charge screening. The distance from where the electron is at in the atom is far away, so we could talk about this distance with Coulomb's law, talking about it either being strongly bound or weakly bound. So what we know about atoms here is you probably know about this. So if I have some type of nucleus, we typically sort of think of atoms as being in shells here, and the electrons living within these shells. So if I truly had a classical atom, if I look at copper, copper has 29 electrons. So if you look at copper, copper has 29 protons and therefore 29 electrons. What you'll find here is that in this shell here, you have this lonesome electron in that shell where the other shells are somewhat filled here. So just by thinking about current here, you could imagine that you could use Gauss's law. So Gauss's law essentially says what? If I was to use a Gaussian shell here, this tells me here, so this is my Gaussian surface. That means that if this is 29, then that means here that the 28 protons plus the 28 electrons, 29 protons plus the 28 electrons, this 29 electrons sees one nuclear charge. So just by charge screening, it's weakly bound. And it turns out that this is the most important, this is the biggest contribution to what makes it weakly bound. Now, the distance for these electrons, as it turns out that as you put in more protons, it actually makes the shells come closer together. So the distance effect is not as strong here, but in essence, you can see here that this distance from here to here is going to be what? It's going to be a large distance. And because that's a large distance, you can see that Coulomb's law says that that electron is going to be further weakly bound. So just by looking at these two things, remember, I can't really do this because those don't really apply to the atom because the atom is quantum mechanical. But you can see how this would be the case. So now I have weakly bound electrons. If I have weakly bound electrons, that means that these electrons now become disassociated with this nucleus. So that means that if I have an atomic structure, let's say it looks something like this, which it doesn't, I'm just trying to make it a little bit easier to see here. If I have some atomic structure, what you'll find here is that associated with each of these copper ions here, those electrons are able to move. And if they're able to move, then that means if I put just a slight voltage across a copper wire, I'll get current flow to move in one direction. So what we say then, now if I put, so this means here I could get current flow with a small voltage drop. Now, the problem is, as you probably already know in 4B here, is that we really don't deal with electrons. We deal with holes. And the convention was set really by the person who developed the galvanic voltage source. And so this we call the conventional flow here, is that we say that these are positive charges, right? Holes and positive charges are the same. So that means here, if I set up a voltage drop where this is positive and this end is negative, then I get that current flow when I talk about voltage drop. That's what we mean by, sort of like a net flow of charge, right? So that's what we call the drift velocity as it moves along that direction. And that drift velocity, as you may already know, is proportional to current. Any questions? I'm assuming you basically understand what I'm talking about, right? Nothing hopefully new at this point. So our definition of current then, right? So if I look at our definition of current, our definition of current is essentially what? It's the number of charges per unit time. So what I mean by that is that I have some cross-sectional area here. If I have some cross-sectional area of a wire here, that means how many electrons are actually passing through this thing here. That's what I mean by current here. And the way we typically write current here is we define it as a function of time here, is that how much current is flowing for this unit time here. And what you'll find here is that it's common practice in circuits to use the lowercase I to define current. Capital I's are typically reserved for phasor circuits, and that represents the amplitude of the circuit. The amplitude of whatever thing that you're looking at, like the current or whatever. And so when I look at a unit of current, we call this an amp. And if we were to look at this in the names of charges here, it's really 6.2 times 10 to the 24 electrons per 1 second. And that's what we call what? Really 1 coulomb in 1 second of time. Now, just to stress this thing that I wrote here in a more clear way here, what we typically find here is that I'll have an element that is a two-terminal element. Now, I don't know what that is. It could be a resistor, a capacitor, or an inductor. And when I look at this thing here, what I'll have here is that I could have positive and negative terminals here, and that just means this here. That if I look at a charge that moves in this direction like this, this is the conventional current flow. That means it's these positive charges. But we don't call them positive charges. It would be holes. As soon as an electron leaves one spot, it decreased the amount of electric charge at that point, and as a consequence, it leaves a positive hole. So I'm assuming you guys kind of talked about this. So if you look at this thing here, if an electron was at that hole and it moves in this direction, and it was right there, if I remove negative charge, that means it's got to be more positive now than negative. And so this is what we call hole flow. And And if you don't consider this direction, then that means, if I look at this terminal here, if this is now negative and this is positive, if I have current flowing in this direction, when I have these terminal drops, then we call this the electronic current. And this is negative charge. That's not the convention. This is the convention. So when we look at our circuits, this is what we calculate. This is not what we calculate. And this is the standard convention. Now, how much charge? You can determine this by just looking at the area of the current versus time curve here. So if I look at I dt equals to dq dt, then this implies here that I can integrate this guy. Let's say if I go from q2 minus q1 will then be the integral of I of t dt, like this here. So this represents what? This is the area of I versus t curve. Since this is a mathematical course in circuits, I'm going to try to inject as much math early on as I possibly can. So sort of like there's no shock value when we get later. So when you look at this thing here, you can talk about what happens if I have a constant current. So if I have a constant current, then that means here, if I plot this guy here, then that means if I have a curve that looks like if this is 1 and this is 2, then this area would tell you how much charge passed through some element here. So then this tells me here that Q2 will then be this area right here, where this is the area right here. So if I start with some Q value where I start with, then it's got to give me that. And you could talk, so if you had like an AC current flow, for example, this makes sense here because now if I have some sinusoidal current flow, you could have a flow that looks something like this. So if I look at a full cycle of AC, then the amount of charge coming into an outlet is exactly the same amount of charge coming out of an outlet. So if I was to integrate to get this area, right? So if I go from here to here, and I look at this thing as being some sinusoidal, let's say I have some amplitude of sine of omega t dt, if I do this over a full cycle, so if I look at the time period where I go over 0 to 2 pi, then that thing should go to 0, telling me that for a full cycle, net charge is 0. So physically that makes sense for an AC circuit here. Okay, so let's talk about voltage. So no, I didn't get into the details for what actually happens in current. I won't go into the details about voltage sources either. But how current flows in a circuit is definitely complicated. And, you know, it's a tricky thing here. So typically, what we do here is that we associate work with the electric potential. Now note, these are two different animals. They have different units. This has units of voltage. This has units of joules. And the way we typically connect these guys here is we think about work as being the charge over a voltage times the voltage difference here. So what you'll find here is that this assumes constant voltage. Unfortunately, if we were to look at this technically, voltage sources do not produce a constant source. What you need also is you need what are called surface charges. So a battery by itself cannot produce the current required in a circuit. You need the buildup of charges along the wires to help you have a constant voltage in the circuit here, which is something that I won't go over here. So, but that's a requirement here. So what we really would have, if we were to really look at what that work is, we would be integrating the voltage. The only time that you have a constant source here is that if you have a constant electric field produced by a voltage source. And of course, that can't be true, right? If you were to look at a very simple power supply, so if I look at like a battery, for example, let's imagine that this is a car battery that looks like this, right? We typically say positive and negative here. What kind of field does a battery put out? You would probably say that it has to be what? A dipole field. So that means here that if I look at my flow, my field here, my field would be going something like this here. Maybe inside I got really tight field line, but then the field must be getting weaker and weaker as it goes along. Is that right? So let me ask you this. If I connect a light bulb to a battery, and I pull it away from a battery, does the light get dim? The answer is no. The battery does not allow that light bulb, excuse me, I should not say that. The light bulb does not get dimmer. Try it. You'll get a kit either tomorrow or Friday. You can hook it up, and you'll see that even though the field gets weaker, the light bulb doesn't change in brightness. That means that the battery alone cannot produce the voltage required to keep a constant voltage. It's a complicated thing. And so what you need here is that you need two things. So in order to produce, well, how do you spell produce? There we go. Produce a constant voltage in a circuit, two things are required. One, you need the battery. right? You need the EMF of the battery, because that's really what you produce at the terminals of that. And the other thing that you need is you need these things called surface charges. It turns out that when you connect a wire to a battery, there are charges that actually go into the insulation and as well as the edges of the wire in order to guarantee that you get that constant flow. So we're done with that then. So moving on. So what you saw in 4B here is that the only way you can produce a uniform potential is if you have a uniform field. So think about that. Does a battery produce a parallel plate electric field? No. Right? That's what the battery produces. And if you had a sensitive enough meter, you could actually measure this field. It would be hard, and you'd have to work your ass off to get it, but that's the case here. And so what you'll find here is that the only uniform voltage is using a parallel plate field. So let me move it further up. How far can I write? Can I write right here? Can you guys see that? Okay, Rory, can you see right here? Okay. So you guys should be okay, right? You should be with bubble. So then if I look at this parallel plate here, if I have a parallel plate, like this, you know that this field should be uniform, assuming that these plates are very, very long. And so if I look in the middle of those plates, then I don't have to worry about the fringings on the sides. So if this is the case here, then this field right here is a constant. So if that's a constant, then you may remember that the voltage is what? Is given by this guy right here. Right? The voltage drop across these plates. So if I look at this voltage drop here, across these plates, it's got to be this guy right here. So if I look at this thing here, what you're going to find here is that, look, that's constant. So if that's constant here, then that means if I integrate from plate 1 to 2, let's call that plate 1 and 2 here, I'm going to get something that's going to be negative E delta S here. Well, let's plot that. If I plot this, what you'll find here, actually, can I not make this S? Can I call this delta X and say this is the X direction? Just because it's a little bit nicer. So if I plot the voltage in one dimension, it's got to look like this here. But look, isn't that a negative constant slope? So what does the field look like now? So in this case here, this represents my potential field. That green is the potential field. So let's look at this thing here now. Why do we calculate potentials? Potentials is the name of the game in physics. It is the goal of physics, is to find the potential of everything. because then we use conservation of energy. And you know how to use conservation of energy. But the name of the game is to always look at the potential field, because the potential field tells particles how to move. So there's two pictures. There's either this electric field picture, there's the E field picture, which physicists typically hate, and then there's the potential field picture, which physicists love. Why? Well, let's think about it. If I have a charge, what's the charge going to do? Well, if I put a charge right here, what's it going to do? It's positive charge, right? So it goes down in this direction. And this picture, what does the charge do? It actually slides down the incline. And if you look at this incline here, let's say that this charge is here. What does that mean? Well, if you look at the total energy of the picture here, you could say that at this point 1, I could then associate a bar diagram that does something like this. It starts off with what? This amount of potential energy, let's say it's electrical potential energy, and if the charge goes, and as you already know, if the charge starts from rest, there's no kinetic energy, but when it comes to this point, what's it going to do? Well, it only has that much amount of potential energy. So the rest of it must be kinetic energy. And so by looking at the picture, you get a good feel for what the damn charge is going to do. So I could do this with any circuit. You could go in and you could look at all of the inclines, right? One of my very classic 4B questions is, if you have a charge that comes in and it sees there's two paths. There's one that's a lower resistance, there's one that's a higher resistance. Which direction is the charge going to flow? The path of least resistance, right? What if I asked you the simple question, why? Your answer is going to be? Probably, I don't know what the hell you're talking about. And it turns out that you got to look at the different potential slopes at each of these intersections. And it turns out when you look at these slopes, it tells you what it does. And that's created a lot by this surface charge, it turns out. But that's what I mean by voltage. So when I talk about voltage, charge always flows from the high to the low potential. And this shape tells us this. But obviously, circuits are way more complicated than this. You'll see me draw a picture like this from time to time, but you know I'm lying. Because you know this is the field right here. It's not this constant field. It's a more complicated field. But we'll say, we'll ignore that. And we'll just say this is what it kind of is doing in this thing. And you'll see that that picture will be very, very useful when we go to power, which we do right now. So probably, when you actually look at circuits, probably, one of the most important ways is actually talking about the power. Okay. So what we want to talk about is we want to talk about power delivered / dissipated. So it could either be one or the other, depending on what is actually happening on the circuit here. And like I said, just as important as the current and the voltage, power is super, super important. Because you'll find out that in circuit design, you'll start to worry about whether the element can handle that much current or voltage. And I'm sure you have burnt out or popped the fuse in a multimeter, and you'll see that when you do that in lab, I'm going to give you the drill, and you're going to change it if you burn it out. So some of you will learn the hard way, and then you'll learn what not to do in the future. So when I look at power here, we know that power could be work / energy. So work and power are directly proportional to work and energy are proportional to the power. It turns out that energy is very, very hard to measure. So the only three things that we measure in a circuit are current, voltage, and power. Power is easy to measure. And the reason why it's easy is we just use the chain rule here. So if I call power P, we can look at W, and note, work and energy are really, right? If you have a coin, one side is power, if you have a coin, one side is work, the other side is energy. They're interconnected to each other. So in circuits, so that we don't choose E, because E turns out in the old days, which is what they used to use for the symbol for a voltage source. So they don't choose E, they use W for energy. But what you find here is that if you just look at the chain rule for this guy here, with charge, now our definition of voltage is how much work per unit charges. So this is by definition voltage, and dq dt is clearly current. And what you'll find here, I should have been careful, here's a differential. No, not a differential element. Here's my differential element T here. And so what you'll find here is that definition of power is this guy here as a function of time here. Now, it turns out that we typically do have to worry about time. So if I look at this guy here, you'll see that I can also get the energy if I integrate this thing, voltage, current, dt here. So this would be the energy. It's very, very rare that I look at the energy. Very rare. But we will look at the power here. But it turns out that this is an important relationship right here. Not so much that we care about the energy, we care about this guy right here. This is the important part. Because when we start to talk about whether a circuit delivers energy or it dissipates energy, we actually look at this guy right here. And so when we look at this thing here, it turns out that elements are either passive or active. And what determines what is passive and active is the integral of the voltage and the current. So we got to look at this integral right here to really get this idea here. So when we say the word passive, so passive is when an element absorbs energy. Whereas if I have an active element, delivers energy. And that's tricky. That could be really, 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 really tricky. So let me ask you this. Well, actually, let's not get there yet. I need to give you a little bit more information before I can ask this question. So what you find here is that, let's go back to this picture. I want to go back to this picture. I'll go back to this picture. Yes.
Maybe I'm getting but when you say absorb, are you saying does it distribute to the rest of the circuit? In that case?
No. No, that it just grabs some energy.
Yeah, but like wouldn't it turn it into heat then?
It does.
Okay, so those would be perfect.
It's not always heat. It could be other things. You're thinking a resistor. Resistor
Yeah, but I'm
definitely.
thinking of like an element that wouldn't let it, that energy then doesn't get to the rest of the circuit. When you say absorb, you're
So
saying it
the-
doesn't get to the rest of
The way I look at it is that I have this amount of energy. When I come afterwards, there's that missing.
to that next part.
Yeah, so the rest of the energy goes to the rest of the circuit. So let's think about passive elements here. So now the first one I'll describe here, and I want to talk about passive. So when I say passive, what do I mean? So if I look at passive, what this implies here is that the current and the E field are in the same direction. Now, I don't really like saying it that way, but I don't know any other way to say it. What I mean by this is this picture. Now note, this is a parallel plate. I'm not treating it as a capacitor, okay? I'm only treating this as a parallel plate. So if I have two parallel plates, I imagine that I have a field that is going in this direction. Now remember, these plates are so far up, they're really big, and I'm only looking at the center, so I don't have to worry about the fringing of the field. So if you look at this E field, it's in that direction. So if I look at the current, then the current flow in this case is going to be in that direction. So when I say that the field and the current are in the same direction, that's what I mean right there. It turns out when this is the case, there is power or energy absorbed by those plates there. Think about it physically. What is the charge on this green charge? It's positive. So what happens when that positive charge hits that negative plate? It has less negative charge. If it has less negative charge, then the voltage drop across that plate must be lower. But if the voltage is lower, then that means that the energy of that element must be lower as well. That's one way of looking at it. The other way to think about it is that you could imagine this. I mean, what happens if you have, some charge that slides down here? Well, does it have potential energy? Yes, at that point. But when it comes all the way down to the bottom, what did it lose? Potential energy. So in this case here, we see that as this charge comes all the way down to the bottom, we say here that the charge lost electrical potential energy. So therefore, it absorbs passive element never delivers energy to the circuit, it only absorbs it. So let me ask you this here. So if I look at this picture here, so then if I have an element here, that means if I have an element, and this is positive and this is negative, and the charge goes, and the current goes in this direction here, because it's going from the high to the low, then that charge must lose energy as it goes through that. So resistors are real clear and obvious. What about capacitors? What happens if I have a charge? Is a capacitor a passive element?
Doesn't it do both?
No. It is passive. Okay? It is passive. Now, charge in a current flow through a capacitor, I'm kind of assuming you've understood that. Now, I may have to go through it more when we get to capacitors, but there are capacitors where they will leak current through. But isn't a capacitor something like this? If I have a perfect capacitor, and I have my wires like this, what do I put inside a capacitor? What's the sandwich in there? Insulator. So we got to be careful how we talk about current flow. Now note, all capacitors leak current. We're not talking about that leaking of current. We're not talking about that current flow. Even though you have to account for it when you're dealing with a real circuit here. There's lots of ways of leaking current through an insulator here. But what you're going to find here is that that current flow better be in this direction for a capacitor. If I have that voltage drop, I have current flow. How do I have current flow? What is that current flow going to do to the upper plate? It causes what? It polarizes the insulator. So as positive charges arrive here, it forces positive charge away from the lower plate, leaving a negative charge. Or you could say here that I could have negative charge flowing in this direction, and then it pushes negative charge off the top. There's a lot to look at that. I won't talk about that. When we get into chapter 7, we may talk about it a little bit more, but it's not important for us right now. But here's my word of warning. Resistors, capacitors, inductors are passive. They follow this convention. And you will be challenged when we get to chapter 8 and 9. I promise you, you will, because you're going to say like, oh no, capacitors are active. And then you're going to solve the differential equation and you're going to go like, why didn't I get the right answer? And it's because it's probably this mistake. So the next one here that we will look at here is active. As you can imagine, if passive is these guys are in the same direction, then this implies here that the current and E field are in opposite. And that totally makes sense here, right? Because, dude, I got just a minute here, so I gotta go fast. So they gotta go in the opposite direction. So if I look at what you learned in 4D, which is this picture, a charge has to go upstream, right, of the field. So if I have this charge right here, and it goes upstream, can the charge do that all by itself? No. What do you gotta do? You gotta work to go against the field. Right? If I look at this thing here, how do I get back up the incline? You gotta do work to get up the incline. And if you do work, what did I do to that charge? I increased its electrical potential energy. In other words, I added energy to the system. And if I add energy to the system, then I must be delivering. And if I'm delivering, it's called active. So what we say here is that if energy, power, is being delivered, then the element is active. That's what we mean by passive and active. You'll find here is that power supplies can be passive. Power supplies can be active. So, okay, I got 2 examples to do, which I will do on Wednesday. I'll see you, unless you're in the Tuesday lab, I'll see you tomorrow.